Namaskar. Welcome to the third day and the final day of 3 days online training program on space technology in disaster management jointly organized by National Institute of Disaster Management, Ministry of Home Affairs and National Remote Sensing Center, Indian Space Research Organization, Department of Space, Government of India. The need to focus on science and technology in disaster risk reduction is also underlined in various important international agreements such as Sendai Framework, Sustainable Development Goals, Paris Agreement, and also in the Prime Minister 10-point agenda, item number 4 and 5, where need to invest in risk mapping globally and leverage technology to enhance the efficiency of disaster risk management efforts has been highlighted. In today's technical session, we will be joined by Dr. Tapas Martha, Head, GGD, GSG, RSA, NRSC, ISRO, and Dr. Shalini Saxena, Malanobis National Crop Forecast Center, Department of Agriculture, Cooperation and Farmer Welfare. Today's technical session will be followed by the valedictory session where we are expecting Major General Manoj Kumar Bindal, VSM ED NIDM, for his concluding remarks. During the technical session, there will be a presentation and each presentation will be followed by the question answer session. Your active participation is very important to us. Kindly use Q&A window only to raise your question. Please feel free to raise your question. Now, move to our technical session. For our first presentation, we have with us Dr. Shalini Saxena, young scientist, Malanobis National Crop Forecast Center, Department of Agriculture, Cooperation and Farmer Welfare. Now, I pass on stage Dr. Shalini. Over to you, ma'am.
Yeah, thank you, Dr. Harjeet. First of all, I would like to thank Dr. Surya Prakash, Dr. Harjeet, and the NIDM for inviting me to speak about the drought assessment. So I'm sharing my presentation now. This is visible to all?
Yes, ma'am.
Okay, thank you. Hello?
Yes, ma'am.
Okay. So
Ma'am, you can start your presentation.
Of this National Crop Forecast Center. This is the technical cell of the Ministry of Agriculture and Farmers Welfare. We are looking after the drought for 17 major agriculture state of the country, and for Kharif and Rabi, we are giving the drought assessment for the country, which is the satellite. First of all, as we all know, that what is a type of droughts or the what is a drought. So I will just give a brief of it, that what are the types of droughts. If there is a lack of precipitation over a region with respect to the normal precipitation, we call it the meteorological drought, and it is based upon the rainfall for over a region. If there is a shortfall in surface and subsurface water supply due to lack of rainfall, then it is called the hydrological drought. And because of the soil moisture deficiency, and when it reaches up to the permanent wilting point and the soil moisture not fulfilling the growth for the crops or the plants in a particular region or in a region or a location, then we call it agriculture drought. Another drought is the socioeconomic drought, which occurs when the demand exceeds the supply of the drinking water and hydroelectric power, such as which exceed the supply. So as a result of weather-related supply shortfall. This is the socioeconomic drought. If we see the overall situation from 1871 to 2015, so there were 25 major drought years. And if we see the top 10 disaster of India from 1900 to 2015, drought is the one of the major disaster of the India. If we concern also with as per the IMD, the most of the states like Western Rajasthan, Gujarat, and these states are chronically drought-prone areas, and parts of MP, Telangana, Andhra Pradesh, parts of UP, Rajasthan, Eastern Rajasthan, and Maharashtra parts. These are states which are prone for, these are frequently drought prone areas. And many of these states are, because now scenario has been changed, but the least drought prone areas are Odisha, Jharkhand, Bihar, West Bengal, and parts of Chhattisgarh, Karnataka, and coastal region of the Maharashtra. So if we talk about the drought management monitoring system in India, so the central agencies involved in this are the first is the Ministry of Agriculture and Farmer. So it's for overall coordination. There is an inter-ministerial crop weather watch group is there, which is leading the IMCT for drought assessment, India Meteorological Department for weather forecasting and for giving the rainfall data. Central Water Commission is for monitoring storage situation in major reservoirs. MNCFC is giving the space technology based drought assessment, and ICR, FRIDA for contingency planning, and with another uh, um, uh, divisions of the ministries are for the watershed development, water harvesting, irrigation, water use efficiency, and of course the National Institute of Disaster Management, NIDM, for capacity. So before going to the drought assessment, satellite-based drought assessment, I will brief about the index which we are using, we can use, or we already have used for drought assessment uh, uh, for the country, or internationally we use it. So aridity anomaly index, which is based on the rainfall potential, evapotranspiration, actual evapotranspiration, taking into account soil moisture condition and using water budget method. It is the percentage of annual water deficit to annual water need or annual potential evapotranspiration. So basically, aridity anomaly index is the departure of aridity index value from the normal, which is expressed in percentage. SPI is the index, which is very important index for assessment of drought. This is based upon the probability of given amount of precipitation on long term of precipitation data, and the probabilities are standardized so that an index of 0 indicates the median precipitation amount. Another index is the farmer drought severity index, and which attempts to measure the duration and intensity of the long term drought. And it actually uses the temperature and precipitation data to calculate water supply, demand, and which incorporates to soil moisture, and it's considered most effective for unirrigated croplands. Another one, we can also consider the crop water stress index, which is to study the water status of the crop. It uses the canopy temperature, and we minus the canopy temperature with the air temperature, and as an index to study the water status of the crops. Surface water supply index is integrates the reservoir storage, stream flow, precipitation types like snow and rain at high elevation into single index number. It takes into found the work done by the farmer with PDSI, but adds additional information including water supply data, and it calculated at the basin level. Effective drought index is a function of precipitation needed for return to normal condition. It uses daily precipitation data to develop and compute several parameters: effective precipitation, daily mean evapotranspiration, deviation of evaporation, and the standardized value of the PEP. So another one is the moisture adequacy index, which is based on the weekly water balance. We use the actual evapotranspiration and potential evapotranspiration to calculate the moisture adequacy index. So these are the some indices, important indices for assessing the drought. So if we uh, uh, consider the drought assessment by international agency, so there is US Drought Monitoring Agency, USDA, that produces weekly map of drought condition that is produced jointly by the National Oceanic Atmospheric Administration and US Department of Agriculture and the National Drought Mitigation Center at the University of Nebraska. These maps are based on the measurements of climatic, hydrologic and soil conditions, as well as reported impacts and observations from more than 350 contributors around the country. The hydrometeorological parameters used for USDM include Palmer Drought Index, SPI, stream flow, and soil moisture, etc. So, also, there is a vegetation drought response index, which is a weekly depiction of vegetation stress across the contiguous United States. Development of West DRI map and associated product is joint effort by the NDMC, the US Geological Survey, National Center for Earth Resources Observation and Science, and High Plains Regional Climate Center. So the West DRI calculations is integrate the satellite-based observation, climate data, and other biophysical information such as land cover, land use, land cover, soil characteristics, and ecological settings. These things are these drought uh, index, drought response index, and the drought assessment by the international agency. So if we see in India, IMD is also giving the uh, drought assessment on the basis of the anomaly aridity index, and also they are giving the standardized precipitation index forecast. They are giving weekly, bi-weekly maps for that. They are giving the statistics for it, and also SPEI index they are also giving. So these they basically denote the water needs of the plants, and the for aridity anomaly index, it is based upon the potential evapotranspiration, actual rainfall, and the actual evapotranspiration. So these index are regularly given by the IMD. Some frequency of meteorological drought, which is based upon the rainfall situation. Maps were generated by the MLCFC. So if we see last 10 years of data or the last 30 years of data, so we can see how frequently drought frequency has been changed from 1968 to 2018, how it's changed. You can see the parts of Rajasthan, they have the high frequency of drought, and parts of Tamil Nadu, parts of Rayalaseema region of AP have the high uh, uh, frequency of meteorological drought. And now the frequency of the drought occurrence has been changed. So this is because of the change in rainfall pattern during the decades. Uh, Mehla, there is a National Agriculture Drought Assessment. Now we talk about the NIDM project, which is the National Agriculture Drought Assessment and Monitoring System. So operationally, MNCFC is giving the drought assessment for the Kharif and Rabi season using remote sensing, and this is as per the guidelines given in the drought manual. So monthly district and sub-district level drought assessment we are giving for 17 agriculture major agriculture states of the country. Uh, Monthly drought assessment report, which is given in June, July, August, and September. And Rabi drought assessment we are giving in month of February. The categories are the normal, moderate, and severe for drought assessment. So many states uh, uses the NIDM's assessment and the data statistics for support in drought declaration. Uh, for Kharif drought declaration, the parameters, it is based upon the two levels, trigger 1 and trigger 2. Trigger 1 is the mandatory indicators and trigger 2 are the impact indicators. Trigger 1 is based upon the rainfall and the dry spell situation. And trigger 2, there are four important index. These are remote sensing, crop situation, soil moisture, and hydrology. So under the remote sensing, we estimate the NDVI, NWI deviation or the vegetation crop condition index. Under crop situation, we calculate the area under sowing, so under the soil moisture, the moisture adequacy index or per percent available soil moisture. Under the hydrology category, we use the parameter reservoir stream, reservoir uh, groundwater uh, groundwater drought index, stream flow drought index, and reservoir storage position. If the two of the selected three impact indicators are in severe category and one is in moderate, then we call the district is under severe drought category. If the two of the selected three impact indicator are in moderate, and if the two of the selected three impact indicator are in severe and one is in normal category, then we call it moderate drought. Otherwise, uh, this is normal. So trigger 2 is based upon the ground truth information or the field data verification. Parameters for Rabi drought declaration as per the drought manuals are there are four major cropping situations are there: rain fed, surface irrigated, groundwater irrigated, and northeast monsoon. So under rain fed situation, trigger 1 or the mandatory indicator are the rainfall deviation and dry spell. For surface irrigation, reservoir storage index. For groundwater irrigation, groundwater drought index. And for northeast monsoon situation, rainfall deviation and dry spell situation are the mandatory indicators. For trigger 2, for rainfed situation, crop zone area, soil moisture, and NDVI deviation. For surface irrigated, we use the crop zone area, NDVI deviation, and groundwater drought index. For groundwater irrigation, the mandatory indicator are the impact indicator are the crop zone area and NDVI deviation. For northeast monsoon situation, crop zone area, soil moisture, NDVI deviation are the uh, impact indicators. So these are the category and the parameters through which we check the metrics for trigger 1. So first the trigger 1 set off or when it is yes, we we estimate the trigger 2 only for those districts where trigger 1 is uh, yes. So then these are the trigger 2, the remote sensing based in vegetation index and the soil moisture and area under sowing. These are the categories is defined under the drought manual. So data which we are using for drought monitoring, for rainfall deviation, SPI, and for dry spell calculation, IMD district level weekly rainfall data we are using. Now we have planned also to give the block level estimates. So for that, we are trying to use a spatial rainfall data also. For crop zone area, deviation from norm, we calculate the deviation from normal. So what is data and ProBA data, fortnightly and derived products we are using. For satellite-based crop condition, satellite-derived fortnightly and derived products, AWIPS 56 meter and MODIS 250 meter we are using. For soil moisture, a water balance model which is developed by the NRSC. So we are using for calculation of PSM. Reservoir levels, we are taking the data from the CWC. For groundwater, post-monsoon groundwater data from Central Groundwater Board. We take the data and then we calculate the groundwater drought index. For various irrigation, rain-fed and irrigated area, DES data are being used. These maps are first of all the rainfall, weekly rainfall, and used to calculate the dry spell situation, and then based upon the rainfall deviation, dry spell, and scanty rainfall. Trigger one has been trigger one. We calculate the trigger one. So trigger one was computed based on the rainfall division, dry spell, and if it is rainfall is scanty, if the district had more than 60% of efficiency in rainfall. Dry spell, and we consider the dry spell if at least for 3 to 4 consecutive weeks from state-wise monsoon normal onset date. Rainfall is below 50% of normal. These maps for trigger 2, if the distance comes under the trigger 1, then we estimate we go for the trigger 2 or the impact indicator. So first is the remote sensing based indices. So NDVI and DWI are the index which we are using for remote sensing based indices. And we take the data from, we use the data of resource set 2 AWIPS NDVI.
Excuse me, ma'am. Sorry for the interruption. Your voice is not clear, ma'am. It's not coming, ma'am.
For soil moisture index, a mean percent available soil moisture we calculate, and PSM indicator is assessed by averaging the consecutive 3 weeks of lowest moisture from state-wide monsoon onset date. So we while calculating the PSM, it does not take into account based upon the rainfall and PET only. Then MODIS and ProBA, earlier we were using the ProBA data. Now because it stopped, so MODIS data we are using, NDVI data we are using to calculate the crop zone area, and we map the crop zone area map, crop zone area deviation map, and generally we take the normal year. So 2016 we take the normal as a normal year, because 2018 2018 was a drought year. So then we see the states which are under trigger 1. We calculate the crop zone area deviation map. Reservoir storage position we take from the CWC to check the reservoir position of the country. So this is the final agriculture drought assessment map, which is categorized into severe, moderate, and normal situation. So for Rabi drought assessment, first we categorized country into 4 cropping situation. Then those situation again categorized into the irrigation and rainfed situation, and irrigated states again divided into the groundwater situation and surface irrigation situation. So these are the situation 1 and situation 4. how we calculate the rain-fed area in northeast monsoon situation, rainfall maps, and then we calculate the dry spell and the scanty rainfall. We take the maximum groundwater level, average groundwater level, and actual groundwater level from a central groundwater board, and then we calculate the groundwater drought for this. This is actually the Rabi drought assessment is a typical very typical process. So then after there is we calculate the trigger one for situation 1 and 4, and for groundwater drought index there is this is the situation 3. Then trigger 1 is based upon the groundwater drought index. Then after final assessment is based on the three impact indicators. These are the NDVI deviation, soon area, and PSM. So how this is how we calculate the Rabi drought for and we assess the Rabi drought for the country. So there is a one drought related data download portal is also available on MNCFC website. One can go through it and can download the NDVI and the WI data, state level and month-wise data, and also sensor-wise data one can download. Percent available soil moisture daily data is also available here. So one can easily download the daily data. Rainfall data, this is a weekly IMD data is also available MNCFC website. So these data are available. So this is easily one can easily download the Excel sheets, and the graphs are also available for NDVI and NDWI. So this is overall from MNCFC side. If any queries, you can please ask the question. Thank you.
Thank you very much, ma'am. Satellite, ma'am highlighted the different indices to monitor drought, like drought severity index, crop water stress index, surface water supply index, and many more. Remote sensing GIS can be used in many areas such as assessment of crop area extent, management of water resources, yield assessment studies, land suitability assessment for agriculture, disaster management, precision agriculture, urban planning, etc. Satellite data contributes on all scales from global through regional to local issues. Thank you very much, ma'am. Now, ma'am, there is
Thank
a
you, Dr.
few
Manji.
questions for you, ma'am. Yeah. Ma'am, there is one question: is can be identified by thermal sensor? Are you there, ma'am? Hello. Yes, ma'am. There is a few questions for you. First question is,
Yes.
yes, ma'am. Is drought can be identified by thermal sensor?
Drought is actually a complex phenomena, and for assessing the drought requires
Hello. Ma'am, next question is, could you please elaborate the methodology for assessing Palmer drought index using geospatial data? Ma'am, your voice is not clear, ma'am.
hello.
Yeah.
So for hello,
Yes, ma'am. Go ahead, ma'am.
yes. So for thermal sensor, is not oh,
I think, ma'am, there is some bandwidth
give,
issue. Thank you very much. Yeah.
am I audible?
Yes, ma'am, you are audible, but your message is not clear.
Okay, then I will write to here what I want to say. I think there is
Yes.
a network issue. Hello.
Yes, yes, ma'am. Yes, ma'am.
Yeah. Yeah. So I will write here in chat section. So
Yes, ma'am.
okay, okay. I think there is some network issue from my side.
Yes, ma'am. We can understand, ma'am. No problem, ma'am. Okay, ma'am. Thank you very much, ma'am. Now we move ahead to our second presentation. We have with us Dr. Tapas Martha, Head GGD, GSG, RSA, NRSC, ISRO, to share his vast knowledge and experience with our participants. Now I pass on stage to Dr. Tapas Martha. Over to you, sir.
Thank you, Ajit. It's good to meet you again. I remember you worked on at NRSC, so
Yes, sir.
enthusiastically learned all the slide Hajar Jonison. I'd like to thank NIDM for inviting me to deliver this lecture, particularly Surya Prakash ji. We are very familiar with each other. So now I'll move on to my slide. Yeah, so you go. I think I'm audible and my presentations is also visible to everybody.
Yes,
Good
sir.
morning to
It's
all
clear, sir.
participants. Thanks. Good morning to all participants. As the topic goes, today I'm going to deliver what is the role of remote sensing, particularly for landslides and earthquake monitoring. As the saying goes, remote sensing is basically eye in the sky. Okay, so when you have eye remotely observing, so you can monitor things very detailed way. Okay, and not only monitor, you can identify their location, their shape, size, etc. That is called mapping. So how do we map landslides and earthquake? We have a dedicated program under ISRO DMSP, and since 2005, NRSC ISRO particularly systematically contributing to various natural disasters. In the landslide and earthquake fields, whatever we have done. Begin with the landslides and then followed by the earthquake. Briefly, as we know, almost 12.6% of India's landmass is prone to landslide disaster. And we are number one in
Hello,
the
sir.
world, unfortunately.
Sorry, sir. Sorry to interfere you, sir. So there is one box in your screen, sir. That is actually blocked. You can see on the sir, right-hand side topmost. So you can drag it downside. Yes, sir. Yes, sir. Now it is okay, sir.
Yeah.
Thank you very much.
Thank you. So to continue, India rank, we rank first in the world for fatal landslides. So we have plenty problem to solve, and we have compiled a database for last 20 years. Mostly, we lost 10,300 lives. That will be in a conservative estimate, and a lot of property and damage also happened. What happens, particularly the bigger landslides? The bigger landslides, they're dangerous, but they don't happen all of a sudden. There are always certain smaller size landslides that are called precursory landslides, and they lead to large landslides when there is a triggering event like rainfall and earthquake. Rainfall is the main cause of landslides in India. Of course, we have few man-made landslides due to road wide activities and then earthquake. these are the activities which we can broadly do from remote sensing data. We can assess the damage, we can map the location that we call landslide inventory, and this inventory data with some weather forecasting, we can also assimilate and do a landslide early warning. And we can find out what is the amount of or the volume of the debris. Okay, that is called volume estimation. We can monitor landslide, and then most importantly, we can map the hazard prone areas. What we call in our landslide term is called susceptibility mapping. So I will go through all these core activities in the landslides one by one. To begin with, this is how the landslide looks on the ground. And if you see the ground photograph, you can very well appreciate that wherever there's a big landslide, there's a loss of vegetation. And all the landslide happens in hilly areas where the slope is steep. And we have very friable rocks are exposed near to geological structures. This is the geospatial landslide inventory of India. ISRO, NRS ISRO, we have been working in this field since last 20 or 22 years, and we have compiled a large volume of data, and that comes to around 50,000 data till last year, and now that has increased up to 70,000. And if you can see our province-wise, particularly the northwest Himalayas, consisting of Uttarakhand, Himachal, then Jammu, Kashmir, and Ladakh. There you find maximum number of landslides. And northeast, though numbers are more, but areas are less because the size of landslides are less from the northwest. And coming down south, particularly in Kerala, Karnataka, and then Maharashtra and Goa, we have lesser number of landslides compared to the Himalayan areas. But particularly the last 3 years, given the high amount of rainfall in southern India, the incidences have increased. And what we did, this national database we have used to rank the districts in the hilly areas. We found total 145 number of districts in the 17 states or 16 states and 2 UTs, which are prone to landslide. And we have ranked them in terms of their exposure to the population, to house, to livestock like animals, and few other parameters. And our analysis shows that Rudraprayag district in the Uttarakhand state is the most prone district in India in terms of landslide disaster. And in the top 10 districts of India, there are 4 districts in Uttarakhand, and then in Kerala also. And Kerala, as I explained before, though we have lesser number of landslides, but the population density and the house density are quite high. This means that the risk exposure is quite high. That's why 4 districts in Kerala are more vulnerable to landslides. Now I'll go to one by one case studies through a few illustrations. What you see now here is particularly the 2018 Kerala disaster. You have a heavy rainfall, almost deviating 100% from the normal rainfall. That led to roughly 5,000 landslides in Kerala, Karnataka, and Tamil Nadu. And you can see we use high resolution satellite data on the order of or very high resolution satellite data, both Indian satellites like Cartosat series and of course international satellites, which we receive through an understanding internationally through international charter, satellites like WorldView and Pleiades. These are the French satellites, US satellites. And we find out what are the places on the road corridor or on the railway track. If you can see here, there is a tunnel which is connecting Bangalore to Mangalore. And we find on the tunnel near the entry of the tunnel, there were landslides. And similarly, also under the highway connecting Bangalore and Mangalore, there are a lot of landslides happen. On the right side, if you can see, I'm moving my cursor over here. This is Kodagu district. This is north of Madikeri, particularly famously known as Coorg for the tourists. And here we have a lot of debris flows happen. And that's basically heavy rainfall. Though the slope is not very steep, but there is heavy rainfall that led to a lot of landslides. This is a case study recently on the 6th August of this year. Unfortunately, we lost almost 70 precious lives. This happened near Idukki, near the Munnar town. And we have a large debris flow, almost 1.5 kilometer long debris flow, which started on the higher hills and it came down. Now there were a few hot pins which were lying where the tea estate workers were staying, and the debris entirely buried those tea estate workers' hot pins, and that to a lot of that lead to a lot of loss in life. And this kind of information we used. This is optical or Indian satellite data, 1.6 meter, and we also used microwave data we received internationally, and all the database were analyzed to find out the size of the landslide, where it started, and how long it was, and those kind of information was provided to the Kerala State Disaster Management Authority. This is in Uttarakhand. If you can see here on the left side, we have the Gangotri Glacier. Near the snout of the Gangotri Glacier, where Gomukh is located, we have a big landslide. And that landslide is particularly on the left side of another valley glacier, which is completely failed. Okay, that has buried a lot of the narrow valley Bhagirathi River, but unfortunately there was no blockage. So this kind of information, quite remotely, it is difficult to go there frequently on ground, and satellite data comes to a lot of rescue here. This is another case study here. Also, Indian satellite data used. This is in Kotropi on 13 August 2017, where we lost almost 43 lives. There was a big landslide which happened. If you can see here, which I was telling in the beginning of my presentation, there were a couple of smaller landslides existing in the crown part. And these smaller landslides, slow facet is under stress. The shear strength of that facet is quite less. And if you have a heavy rainfall, then the pore water pressure will increase, and that will lead to a bigger landslide. So these kind of big landslides are not happening all of a sudden. That much I can tell based on our analysis for last 50 years, maybe years, a few more landslides also in Montam, Sikkim also. You find there were existing smaller landslides, and they are led to large landslide and further loss of life and property. So how we do, this is the technique which we employ here. We have the satellite image before the disaster. Then we have the satellite images after the disaster. As you can see, there are a lot of bright patches, and their tonal properties are quite unique, and their shape also quite unique. And all those features to map and identify landslides after the disaster. We call this as an event-based landslide. Particularly in this case study, which I am displaying now, it happened on 14 September 2012 in Okimot, where 51 people died, and altogether we mapped around 473 landslides. We not only rely on one set of pre-disaster and post-disaster data sets, we have access to multiple satellite images, both our ISRO sources and international sources. That helps us to improve the masking due to cloud cover, the masking due to topographic shadow. If you can see here we have a landslide which is visible in August, but it is not visible in December because we have a low sun elevation angle. That's why it is under topographic shadow. So we use multiple multi-season satellite data, high resolution nature to identify all the landslides. We have also developed a mobile app, okay, and that mobile app is also available in a free format in our Bhuvan portal, where anybody can download. If they have a little bit information about the landslide disaster, they can use that. It is an Android-based app. They can use it and collect data in any remote areas and send it to us. So it will help us to find out many smaller landslides which goes unnoticed. And that kind of rainfall information, if it is available, it goes down information, and that can be used for rainfall threshold modeling for early warning purpose. So this is the interface of the mobile app, Android-based mobile app, which is called FLIM, F-L-I-M. That is Field Landslide Inventory Mapping. So this app have a lot of it is carefully designed. We have also drop down like type of landslides and the history of landslide, what is the material involved, how it occurred, what are the things it affected, what was the rainfall on that time. There are something like 18 set of information which you can feed to the mobile app, and it is the moment you enable your GPS, so all that information you are collecting is also geotagged. So that's a lot of information where a responsible citizen or any researchers working in the landslide domain, they can contribute. This database will be populated in the Bhuvan portal, and there is a question, what is the name of the app? It is called FLIM, F-L-I-M. Okay. So this FLIM app is available, freely downloadable in Bhuvan portal. If you can write to me also. Okay, given the large number of landslides which happen after major disaster, if you our Uttarakhand disaster that has almost triggered 6,000 plus landslides, the Kerala disaster that has triggered almost 5,000 landslides. So many landslides, we need to map satellite image. We are in advantageous position because we can see the area and we can map it. At the same time, as part of rapid response, because NRSC is a nodal agency in India as declared by NDMA to map landslide in rapid mode. So we have developed an automatic technique also to identify rapidly those landslides so that we can quickly disseminate the landslides so that we listen to the ground authority. Object-based image analysis technique wherein we first segment the image. I am not going detail into the image processing, but what I can tell you is that the image which we are seeing here, the bright patches, they are the landslide, but all the bright patches are not landslides. So what we do, we try to group all those pixels into segments. If you can see right now down below, we have yellow color polygons, and each polygon is having a different color intensity. So we use the color intensity values, the texture values, the image texture values, and then the slope characteristics to identify, classify whether they are landslide or non-landslides. This kind of image thresholds we have developed, our NRC has developed through a research program where we have threshold of slope angle, stream ordering, and then NDVI, and then GLCM, and the brightness of the image, a few morphological relationship. Some of them are the shape relationship together to identify landslides, and we have mapped those landslides up to 7% range. Okay, so these are the landslides which are identified automatically. The purpose is, as mandated by the government of India, we should rapidly identify them and give it to the stakeholders. There will be some kind of error in that. I'm sorry. There will be some kind of error in that, but that can be eliminated in the subsequent stages. In this slide, what I'm showing is that you not only map the landslides, but also you identify the type of landslides. The landslide types like debris slide or debris flow, it can be rock slide. Those type of landslides can be classified using additional information from the cartodem. So we in India, we have 10-meter cartodem, and that can be used to identify different types of landslides. Typology of landslides, its identification is very important. Why? Because depending upon the type of landslide, our ground mitigation measures are dependent. So that's why this kind of value addition to the landslide identifier is very useful. This database, whatever we prepare, we have submitted to NDMA. We have submitted to GSI. GSI is nodal agency. GSI is nodal area for landslide mapping. So this database has gone to GSI also. The algorithm which we developed using recognition software, and it consists of few steps where we mostly employ the image processing techniques and the derivatives which were derived from high resolution satellite image and like NDVI and principal component. From the DM, we derived the slope angle, the flow direction, the slope aspect. There are multiple parameters has gone into this algorithm to identify the landslides in an automatic way for rapid assessment. These are the steps how the algorithm produces results, and different steps like identification, segmentation, and finally classification. Then you can see the first step, we identify a potential landslide, and then we evaluate whether the segments are correct or not. In the second stage, we have further improved the segments. Once the segments were clearly identified, then the classification routine runs. And in the final step, you can see here the landslides were classified as rotational rock slides or translational rock slides. Now we'll go to volume estimation. That means if there is a landslide, it has come down, either it has blocked a major road or it has blocked a major narrow river. Some temporary damming has happened. There is a chance that the damming will be fixed and there will be a further flash floods downstream. So how to identify the volume of the landslides? So we have, you can see here, we have a cartosat one image. On the left side, you can see we have pre-disaster landslides. On the right side, we have post-disaster landslides. So, unlike the landslide inventory mapping, wherein we use the multispectral or panchromatic image for preparing the location and mapping the landslides, in the volumetric analysis, we use the pre-disaster and post-disaster DE. Okay, and then we employ the curtain field analysis in GIS. Find out what are the areas there is a volume loss and there is a volume gain. If you can see this figure, the gray color corresponds to volume loss. So in terms of the landslide terminology, that is called zone of depletion. And then we have this pink color which corresponds to volume gain, that is called zone of accumulation. What is the drop in the elevation also we can find out. You can see that near the crown part, we have roughly 33 meter loss in elevation, and in the down part, we have roughly 39 meter gain in the elevation. So this kind of multi-temporal DEM has been used to find out the volume. And in this case study, we found that the volume is almost 0.5 million cubic meter. This is another case study. This is quite interesting, wherein we have detailed collaboration with CWC, with NDMA. This area is very remote in the Zanskar Himalayas in Jammu and Kashmir. This is located at an elevation of almost 4,000 meters. It is very difficult to go there, even by air also. So we have used multi-temporal DM, and we find out the volume, how much volume. This is a Fuktal River landslide. The volume of the landslide is 2.7 million cubic meter. And you can see this is the road, Fuktal River flowing in this direction. This part is the blocked. This part is the blocked river valley. And the volume which I have just now told, 2.7 million cubic meter, this corresponds to the amount of debris which is lying on the narrow river valley. And because of the blockage, there was a long lake of 17 kilometers. 17-kilometer long lake was created in the upstream side of the Fuktal River. Then we can use satellite data to find out what is the cause of that landslides, particularly remote areas. The case study is very well known. I mean, I have also presented this before to a lot of my students and a lot of participants also. This one is particularly for the 2013 Kedarnath disaster. If you can see, this is a Choravari lake, which is also known as Gandhi Sarovar. And this lake was breached. And you can say this lake embankment is lateral moraine. This lateral moraine is nothing but a moraine of the Choravari glacier. This is a non-lithified moraine. And when this lake was filled to the brim, and moraine got breached. You can see here this part, the moraine got breached, and that's how all the water in the lake came downstream. And exactly in the downstream, we have famous Kedarnath temple, and all the water hit there. Okay, so now we have used multi-temporal satellite data to reconstruct the history of the landslide with the available information of the local people. We found that, if you can see here, I'll go to my next slide. Yeah. So we found that there are two events which occurred in the June 2013. The first event was on the night of 15th June. This happened on the right side, on the eastern side of Kedarnath. This is the Kedarnath temple and city town. On the right side, there was a, and on the next day morning, there was a beaching of this Gandhi Sarovar lake. And the twin events led to a lot of damage. As you know, more than 5,000 people were killed. A lot of hardship happened to the tourists, and a lot of untold stories have you must have seen. And the Mandakini River, which is originating from the bed of the river has been elevated by almost 12 feet because that much amount of material has been eroded from the upstream side, particularly the glacier regions where moraine deposits were available. And then coming to the damage assessment, we have again this, you can see here the Cartosat 2 image, very high resolution image, individual buildings are seen here. And the circle in the red highlights the Kedarnath temple on the left side, and side the Kedarnath temple after disaster. Kedarnath temple is standing as it is, but the Mandakini river has changed its course. If you can see the right side, Mandakini was flowing on the left side or the western side of the Kedarnath town before the disaster. And now in the image you can see here, it is lying in the eastern side of the Kedarnath town because this flow, natural flow path has been blocked by the Day-3 which has come from the upstream side. So this kind of cause analysis or damage analysis has led to even the change in the river course also in the upstream side. Area where the famously known as Rambara, when you travel from Sonprayag to or the Gaurikund, from the Gaurikund to Kedarnath, is a place called Rambara. And these red colored dots corresponds to the houses which were existing and which are no more. The bright color in the image, you can see that these are the erosion which has happened due to the rise in the water level of Mandakini river, and all the houses have been washed out. So this kind of damage analysis can be done when we have high resolution satellite data, and this kind of information is very useful for district authorities since the area affected is quite limited. This is another case of 2012 Okimot disasters. As you can see, on the flow path of the landslide, there are buildings. So they are completely agricultural terraces, slab cultivation is going on, and there are a couple of houses over here. And when there is happening on the upstream side and it is on the runout path, this will be buried. The same thing happened here, same thing happened in Kerala, and same thing happened in other places also. And the second slide also, you can see this is Chunni and Mangali village in the Okimot Tehsil, wherein almost 53 people were killed because the village was buried. 70 to 80% of the houses in the villages were buried. There was a landslide in the upstream side. Coming to monitoring part, as I mentioned that eye in the sky, we have multi-temporal satellite image, list for data which we mostly use. It has a good swath of 71 kilometer and it is resolution is 5.8 meter. This is mostly used. The repeatability of the satellite is 24 days, but we have an option of emergency programming. When there is a major disaster, we program the payload of the satellite and we can get the report data in every 4 or 5 days. Here, this is a case study in the Sunkosi in Nepal, because the Kosi River comes to India and this does a lot of devastation, particularly in the state of Bihar. So there was a mandate by the government to monitor this landslide in the Kosi River. So we have used 5th August image, then we have used 9th August, followed by 13th September. There are multiple images we use, I have not shown here. And we can see that there was a water impoundment in the upstream side. The lake was formed You can see from this image of 5th August to 7th September, the impoundment area has decreased because the water has been, the temporary landslide lake has been breached here uh, to allow the flow of water downstream so that flash flood can be avoided. So this kind of monitoring will help the authorities to reduce the alert level in the downstream side. This is another case study for monitoring in the Fuktal River. We have used Cartosat 2. This particular event we have monitored almost for a period of 5 months. So a lot of resources goes, a lot of analysis, lot of satellite data. We use it. You can see 20 January image. Then we have 25th January. Then 21 February. The water level is increasing slowly. Okay, from this image to the next one, the water level is increasing slowly. That shows that there is a potential threat level a little higher side on the downstream side. But fortunately, the debris which blocked the river was also breached, and it allowed the water to run out, and there was not much damage. Of course, there was damage to the property, but there's not much damage to the people or deaths to the people. Yeah, the susceptibility mapping. Hope I am, yeah, I have time. Yes. So this is susceptibility mapping. Susceptibility means to find out what are the areas prone to landslides. As you know, you must have traveled through hills. You find that certain areas the landslides are occurring frequently, certain areas are safe. Why so? How it is happening? What is controlling? This is nothing but done in the susceptibility analysis. In this analysis, we use lot of parameters. Current parameters like what is the rock type, what is the slope angle, what is the geological structure, land use type, then you have lithological properties. So all these properties were used and we do a statistical model. By doing the statistical modeling, we find out what are the areas geographically that is safe and otherwise unsafe. So if you see this map, we have 1 minute. Okay, if you see this map, we have this city of Aizel in Mizoram. We have mapped the susceptibility and categorized the entire district, the district of Aizel. Categories: low, moderate, and low, moderate, and high. So high categories, particularly those red color things, are the areas where the chances of occurrence of landslides are quite high. Okay, so I again tell these are the areas. I am not telling in those areas when the landslide will happen. Okay, so that comes in the domain of early warning. I can only tell in this process this X area is good, safe, the Y area is bad, unsafe. This is a good information for the planners to design their future developmental activities. And this kind of information we did, NRSA did in the 2001. Particularly, there was a requirement from the government of India, and we have identified major routes in the Himalayan state, particularly Uttarakhand and Himachal Pradesh. The routes, whatever mapped and the radar donation maps are prepared, they are freely available in the Bhuvan portal for visualization purpose. You can see the Kedarnath town, which is located here, they are mapped, they are under high category. Okay, so high, very high, and severe category. These are the category where the chances of occurrence of landslides are quite high. So this kind of information was mapped, atlas was released, and it was distributed to the stakeholders in both the states. And similarly, we have also mapped in the northeast, particularly for the Shillong to Silchar, the route connecting Shillong city to Silchar, Shillong to Aizawl via Silchar, that has been also mapped. Now coming to the early warning part, look at the slide. This is the figure we have done the field work last year. This is a place called as Puttumala. This is a place Puttumala in Kerala. And there's a big landslide which happened sometime in August 2019, and that led to almost 16 people were killed, unfortunately. The runout of the landslide was more than 2 kilometers. Okay, so what exactly happens? Why it happens? The landslide, why it happen in the rainy time? So it depends on how much amount it is raining and for what duration it is raining. Okay, so that we call as intensity and duration of the rain. So not only the rainfall amount on, but how it has been raining for days. That is called as antecedent rainfall. So daily rainfall and the antecedent rainfall, if you can model, then you can be successful in the landslide element. It is sounds so easy, but actually when you practice and implement, it's very difficult. You need a lot of past information, the occurrence of landslide in that area. Okay, and actually the pore water pressure, as you know, there are soils, there are cracks in. So when there is rainfall, the water goes inside those pockets of pores and increases the pressure. That means it pushes the rock or soil outward in the slope, and that leads to the decrease in the shear strength of the soil or the rock. We can do a monitoring on the ground using piezometer and using several instruments, but that will be a Herculean task because we have a lot of area, vast area prone to the landslide. Sorry. But what we can do, we can empirically model the rainfall, okay? And that rainfall we can find out for particular area, particular catchment, what is the amount of upon the soil type, rock type that is leading to the landslide. So we can do a regional landslide early warning, not a site specific, but it can be very effective. That is what NRC has done. We have a this is a flow chart. I can explain. We have a landslide database which consists of new landslides and old landslides, and then we have a rainfall. We have a historical rainfall. Sometimes the actual rainfall data comes from the IMD's rain gauge stations, and it also comes from satellite-based observations about actual information. And then we have also models, WRF models by IMD, and we have ISRO. We have also our own model where we forecast rainfall for next 72 hours. So the actual rainfall and the forecasted rainfall. So these two parameters, they are combined in a rainfall intensity duration analysis using the rainfall thresholds which we have already arrived, and that is used for a early warning purpose. So that early warning is given in the Bhuvan portal. You can go to the Bhuvan portal of NRSC. We have a disaster link. The moment you go to the link, you will find this kind of landslide early warning now. This case study which I am showing here is that this is part of I think Simla somewhere, where we have used the susceptibility map and the rainfall information, which is a forecast rainfall information, and given a daily early warning for 3 days. That means if you go today to the Bhuvan website, you can see what is the early warning status. That is red color, one category, orange color, watch category, and yellow color advisory category. And these three types of colors are available for coming 3 days. Some validation we have done, and this is available freely. You can also use it and validate, saying that actual occurrence of landslide information using the Fleam mobile app, which I have explained before. This kind of information route wise is also available. This is a route which is connecting I think it's Rishikesh to Kedarnath and Badrinath. Okay, so this kind of information is available in Google portal. Since 2015, this early warning is issued, but we call it as an experimental early warning because it has not been sufficiently validated. But as you know, GSI is a leading agency in India, or the nodal agency in India for entire management of landslide disaster. So GSI is currently developing few models, and we are also going in a collaboration mode to provide all kind of satellite-based information using optical images, using microwave images, using satellite interferometry techniques. So this kind of collaboration is going on, and very soon we'll be having a better landslide early warning system for Indian landslide prone areas. Okay, with this, I have come to the end of my landslide part. Now I'll move on to the earthquake part. Okay. So earthquake part, to summarize the activities in NRSC are mostly limited assessment. That means when we have a big earthquake, there are a lot of house feature damage we identified where are they, and we also do some kind of interferometric studies. We have some GPS data available. We do a crustal deformation, how the Indian plate is moving. In this slide, if you see here, okay, this is seismic hazard prone areas in the world as well as in India. You can see earthquakes, they occur only in the plate boundaries. To a geologist, I need not explain this, but to non-geologists, I can say that, or to non-earth scientists, I can say that, and the world consists of several plates. Some are major plates, some are micro plates, direction. So when they are moving towards each other, that is called a convergent plate boundaries, we find lot of these red dots. Okay, a lot of these red dots are nothing but corresponds to the plate boundary where the chances of occurrence of earthquakes are quite large. And our seismic hazard donation map has been prepared by India, and we can see that we have categorized India into 4 zones, starting from zone 2 to zone 5, and most of the Himalayan areas and in the western part of India, Gujarat, Kutch region, and northeast part, they are under the highest category. And there also we see a lot of landslides happen. And this is how we are telling particularly to the Indian tectonic setup. As you know, our Indian plate is moving northward, or to be precise, northward, and it is going under the Eurasian plate. Okay, so if you see the sketch down below in this section, this is called as main frontal thrust. Okay, so the main frontal thrust, here it is a rigid movement, and you go deep inside mantle, it is a ductile movement. And this is a place where, as you can see the red line, this is called as locking zone. Okay, the locking zone, that means where the Indian plate is not moving smoothly, it has been locked. And the stress which is accumulated in this zone, they are released periodically and leading to a large earthquakes. Okay, the major earthquake releases a lot of energy, followed by aftershocks, so that subsequently slowly releases the energy. Okay, and from remote sensing data, we can identify a lot of regional geological structure, some of the active faults also in the mountainous regions. This is a Doon Valley picture, Doon Valley satellite image. You can see that on the left side we have a Yamuna tear fault, and the right side we have the Ganga tear fault. Okay, this is Dark Pathar, and this is Dehradun city, and you can this is sorry, this is not Dark Pathar, this is downstream. It's happening and other places, and this is where the Yamuna got across the Shivalik range, and this is because we have a Yamuna tear fault. Similarly, in this side also we have Ganga river which is coming. This is a Ganga tear fault. And if you go regionally also, we can find out the major faults in the Himalayas. As you can see here, the Karakoram fault it can be mappable here in the Himalayas. And we can find out the active movement. You can see here there is a strike sweep movement and a lot of linear striking features in the alluvial plan you can see, and some sort of wet patches you can see. These are particularly the areas where liquefaction is happening. Okay, so these kind of features can be mapped using the satellite data because you have a synoptic view. This area collecting information for each point is very difficult. So this kind of a priori information can be collected using satellite data and can be interpreted for earthquake studies. This is, you can see so many earthquakes. We have a lot of clusters over here. Delhi, this is the Moradabad beach, and here also in the Palwell flexure also we have Mumbai. There are a lot of we call it the earthquake swarms. So a lot of earthquakes are happening here, but the major earthquakes are particularly those strong earthquakes are greater than the moment magnitude of 8, which are shown with the red color dots. Okay, so they are less in number, but they are highly damaging. One case study, like I have done for landslide, I'll also do for earthquake a case study. That is the April 2015 Nepal earthquake. This is a large earthquake. Many parts of India, particularly the Gangetic Plain, in the state of Bihar and Uttar Pradesh, they also witnessed a lot of ground shaking because our site, particularly, is alluvial plain where the earthquake waves travel very fast, and that's how. But unfortunately, there was not much damage, unlike it happened in the Nepal near Kathmandu. You must have noticed a common phenomena, which is right practice after the earthquake. When there is shaking, people try to come out, and if the shaking continues for long, they try to stay for 1 or 2 days outside. That's exactly we noticed in the Nepal earthquake. You can see there is a playground. This is a big playground near the Tribhuvan airport in Kathmandu, and you can see this is empty. I mean, empty means there is nothing picture you can find out. On the right side image, you can see after 2 days, lot of temporary camps have been established here. People are staying here. Lot of white color dots you are seeing, patches you are seeing. There are temporary camps where people are staying. And there is a famous tower, Hara Tower, which was damaged. You can see this is a high resolution image. We got it from France, satellite from France. You can see this side, you can clearly see the tower with the shadow, and on the right side, you can see the debris only. The field photograph which is shown here is we collected when we have gone to Kathmandu as part of Indian mission, and we have visited many places, and we see that a lot of places have been damaged. And similarly, here also, the Cartosat 2 data shows a lot of buildings in the Kathmandu and surrounding areas, Bhaktapur has been damaged due to the Nepal earthquake. And this is a Darbar Square, is a famous tourist spot in the Kathmandu city itself. And you can see the pattern of the houses is completely different. Okay, and this is further a high resolution 0.5 meter image. And you can see that this is particularly not RCC structured buildings. They are all with the bricks and with the wooden logs. They have created these buildings, and they have completely collapsed, particularly here. This is, you can see the building collapse again with high resolution satellite data. So this lot of information remotely also. So NRSC has contributed a lot to map the landslides, as well as to map the buildings also. In this part, this particularly the building in the yellow circle is standing here before the disaster, and in the right side after the disaster it has collapsed, and it has collapsed on the road itself. So that means any relief and rescue party cannot go through that road. So we need to give this kind of information. That means what are the areas where road is clear and the ambulances or the relief party can go there also. These are the photographs that we collected when we have gone to Kathmandu. You can see the Darbar Square and the PMO building in Nepal. A lot of Hanuman Dhokka, which is particularly very interesting and popular tourist sites, is entirely collapsed. And this kind of information we have also mapped before going to the field using high resolution satellite. This is another interesting part, quite remote in Nepal, bordering Tibet. We see that a lot of landslide also happened, particularly 15,000 landslides we have mapped in this event. And we see that happened, and this information was passed into Nepal government. And I understand when we went there that they have study and they have gone to this area to see whether this lake is still there. And you can see there is a dam lake. There is a dam lake, and there is a potential flash flood in the downstream. So this kind of information was not available to them, and through case studies like this, through satellite-based analysis, we have provided this critical information. This data set, so we have also mapped individual buildings that were collapsed using our own ArctoSat 2 satellite data. The red color patches you can see fully collapsed, and the yellow color polygons or patches you can see there partially collapsed building. So this kind of building collapse also mapping can be done using a very high resolution satellite. One I would like to say that how space technology can contribute more in future years is using satellite SAR interferometry. SAR interferometry, wherein we use a phase information in the microwave satellite data. The phase information will precisely tell in the millimeter level whether there is a movement in the Indian plate towards south, towards northeast. Okay, and in the aftermath also we can find out this case study, particularly if you can see the red color patches shows that the areas near Kathmandu they have gone up by almost 1 meter. Okay, and the areas north of Kathmandu they have gone down by more than 1 meter. So not only it has shown the vertical displacement, it has shown also that towards south laterally, Kathmandu has come closer to India. Almost in the order of 1.7 meter, if I remember correctly. This figure has been taken from literature. You can read for that. But in future, now India and USA, they are coming up with the L-band mission called as NISAR mission, NASA ISRO SAR mission. So this mission will be most likely be launched towards the end of 2022, and this database will be available freely to all researchers community, to everybody who wants to use. And through this database, through this satellite, we can find out in what rate our Indian plate is moving. Okay, and we can also use similar technique also to locally map in case of landslide at what rate a particular part of slope is moving, whether there is a slumping, there is a creeping happening. So this kind of information can be also mappable coming to the NISAR mission. So this mission is an L-band mission. There are a lot of advantages compared to C-band mission, and everybody in the world community is quite hopeful about this mission. And this will solve, or this will address a lot of issues, the data gaps which we are facing right now. With this, I will end my presentation right here. I hope I could make some sense to the landslide and earthquake disasters, whatever we are doing at NRS ISRO through our DNS program. Now over to you, Harjit, and if there are questions, I will take them.
Thank you very much, sir, to enlighten our participants about case studies of satellite-based landslide mapping, namely Kerala disaster, Gomukh landslide, Kochupi landslide, and how the landslide inventory mapped through automatic method and important stages to map landslide. Sir also highlighted how to damage assessment, susceptibility mapping, and early warning assessment by remote sensing and GIS for landslide and earthquake hazard. Thank you very much, sir. Sir, there is so many questions for you, so I'm asking one by one. First question is, in comparison to the Himalayan region, the Deccan Plateau is the most stable region of India. As well as here, we can expect less impact of earthquake. But what are the main reasons that trigger landslide in the southern part of India?
Yeah, so as I've explained, for the southern part of India, particularly the state of Kerala, Karnataka, rainfall is the major triggering parameter. So I think if you look at the northeast Meghalaya region and followed by the western Ghat part, it receives a lot of rainfall. So lot of rainfall means the terrain has, and we have a lot of loose materials in the form of regolith available. So whenever there is a heavy rainfall, then the shear strength of the soil decreases. So that's why we see a lot of landslides in the southern part.
Thank you, sir. So next question is, could you please elaborate the object-based classification for landslide inventory?
Yeah, I can elaborate that, but it's not easy in a short time. I can tell you that, we have a pixel-based method, and then we have an object-based methods. So the landslides, as you see, they are not governed by the regular size of pixel, like 2 by 2 meter. So we use a segmentation method. So we group all the pixel into a particular homogeneous unit called as object. So once we have that object, then we use the classification technique. We use the shape, like it's a long object compared to the width. We use the slope direction, slope angle, the NDVI, the principal component, and the flow direction. So these are the additional parameters which are used. We have done a lot of research work. I suggest those participants, they can go through our research profiles, and if they can write to me also, I can give some literature so that it becomes very clear.
Thank you, sir. And I want to add one thing to the participant that during my research work in the PhD, I have learned these technique from. So it's my privilege to have you, sir. Thank you very much, sir. And next question is, sir, is there any model which could be used for mud flow and debris flow analysis?
There are a few open source models are also there. Few commercial models are also there. You can see that commercially we have RAMS model, which we are using for debris flow analysis, and open source we have flow or 2D, then Dan8. I mean, you can Google around, you will find a lot of models available. It can be easily done. Yes, it can be done.
Okay, sir. So, and the last question is, do you think SAR remote sensing can provide us better information to landslide prone areas rather than optical remote sensing?
Yeah, I would say this is a very good question. I mean, look at the evolution of SAR image. Okay. Sometime back, 25 years back, when we started, we have only ERS1 and ERS2, followed by JERS. Then now it has been much more popularized with the availability of Sentinel-1 data. Okay. And in future also, of course, we have ISRO research satellite. Okay. In future also, NISAR is coming. So we have to look the landslide problem slightly different. Okay, the way we look at the landslide problem when we work with optical data, we can't do that way because handling my completely different. Okay, we have to use the phase information which is available in the microwave satellite data, and we have to use that by multi-temporal interferometric technique to find out at what rate that particular slope is moving. We are doing some R&D studies, and the results will be out soon. Internationally, there are a lot of studies has been done, and in future, for early warning purpose, SAR interferometry is going to play a key role. Of course, there will be good support with the optical remote sensing data, but SAR interferometry is going to play a key role in future.
Thank you very much, sir, to be with us. Thank you very much, sir. Request my colleague, Mr. Anil Kathat, YP NIDM, to propose summary of the training program.
Thank you, Dr. Ajit. I am audible?
Yes, sir.
Parts. Program on space technology, disaster management, the joint venture,
Sir, it's
disaster
better to
management,
turn off
Ministry
your
of
video.
and Center Space. The point of okay. This is clear now. Hello.
Now, sir, it's clear. It's clear, sir.
Okay. So the aim of the training program was to foster the point 5 of Honorable Prime Minister's 10-point agenda on disaster risk reduction, and that is leverage technology to enhance the efficiency of our disaster risk management efforts. A platform that brings together organizations and individuals and helps them map and exchange expertise, technology, resources that would go a long way in maximizing our collective impacts. Space technology is the weapon that can be used in all phases of disaster management, from preparedness, prevention to response and rehabilitations. The most important one, the effective forecasting and early warning system, and example is cyclone. The technology has helped us to flatten the graph of fatalities in episode of cyclone. We need to increase such efficiency of early warning system for all other major disasters through the application of space technology. NIDM has also been endeavoring in this front and has established India Disaster Resource Network, a web-based platform for managing the inventory of equipments, skilled human resources, and critical supplies for emergency response. To enable the decision makers to find answers on availability of equipments and human resources that require to combat any emergency situation. This database will also enable to assess the level of preparedness for specific disasters. The context of this 3 days online training program was set through the opening remarks by Professor Surya Prakash, Head GMR Division NIDM, and by keynote address of Sri Santanu Chaudhary, Director NRSC ISRO, during the inaugural session on day 1. Further, it was concreted by our technical session experts, namely from day 1, Dr. Manjul Hajarika, Asian and Pacific Training Center for Innovation and Communication Technology for Development, Professor C.V. Western, Department of Earth Systems Analysis, Geoinformation Science and Earth Observations, University of 20 Netherlands, and Dr. K.H.V. Durga Rao, Group Head, DMSG and RSC. On day 2nd, the expertise and experiences on the theme of the training program was shared by Professor V.S. Rao, Center for Studies in Resource Engineering, IIT Bombay, and Mrs. Sri Lakshmi, Head, EDSS and RSC. On the 3rd day, that is today, Dr. Salini Saxena, Young Scientist, National Crop Forecast Center, Department of Agriculture, and Dr. Tapash Martha, Head GGD and RSC, provided insightful deliberation on application of space technology in managing the risk of disasters. And we hope that this deliberation from our experts enrich the knowledge and capacity of all the participants apropos of space technology in disaster management. With these words, I hand over the mic to the moderator. Over to you, Dr. Harjeet.
Thank you very much, sir. Now I would request Professor Surya Prakash, Head GMR NIDM, to propose the concluding remarks of the training program. Over to you, sir.
Thank you, Dr. Harjeet. We started on day 1, that is on 7th of October. And we started with a good beginning because of the day 1, we had a director NRSC as part of our inaugural program who has actually shared his experiences also. So we were motivated not only by his presence, but also by Dr. Manjul Hazarika as well as Kisven Western, who has done a lot of contributions in the field of space applications for disaster risk reduction, whether it is landslide, industrial disaster, or any other hydrological disaster. So we are happy that we have got resource persons from IITs like CSRE, IIT Mumbai. We had got experts from ITC. We had got experts from UNSCAP Center on special technologies, and also from MNCFC. So we had experts and good contributions from their side, and they shared their rich experience as well given exposure to our participants. So I hope this training, as I'm learning from the chat box as well as feedback from the participants, would be very useful in their own works and would also help us in our efforts towards making our country disaster free and with reduced disaster and resilient communities. So I thank you all, the team members of organizing team, who has taken all the troubles to communicate, to plan, to execute. And also in between, there were some hitches and problems even in the Cisco web platform. So you have all managed it well. I would like to communicate my personal thanks as well as thanks on behalf of NIDM to all our experts, resource persons, all the delegates and participants in this program for making it a great success. And also thanks to our team of GMRD, which has also not only moderated but also facilitated the hosting of the program, and felicitations. So thank you all, and I wish all the best to you for the further programs. Thank you.
Thank you very much, sir. It's my privilege to have been asked to propose a vote of thanks on this occasion. I wish to express my sincere gratitude to Shri Shantanu Chaudhary, Director NRSC ISRO, Space Department, Government of India, for sparing his precious time from his busy schedule for providing encouragement and support to all of us in the inaugural session. And I also extend my thanks to Dr. KHV Durga Rao, Group Head, GMSG, RSA, NRSC, and Professor Surya Prakash, Head GMR, for his presence and also for his enormous cooperation and support in organizing of this training program. I wish to express my gratitude to Major General Manoj Kumar Bindal, Executive Director, NIDM, for his encouragement and support in our every endeavors. I must mention our deep sense of appreciation for Professor Weston, ITC Netherlands, Professor Manjul Hazarika, Director APCICT, Professor Y.S. Rao, IIT Bombay, Mrs. P. Sri Lakshmi, NRSC, Mr. Anil Kathat, YP NIDM, Dr. Tapas Martha from NRSC, and Dr. Shalini Saxena from Malanobis National Crop Forecast Center for their presence to enlighten the participants with their vast knowledge and experience. I also extend my thanks to NIDM team, Mr. Anil Kathat, Mr. Raju Thapa, Balaji, Gaurav, and Shobhit, to make this event successful. And for the participant, I want to say that feedback link is shared in the chat box. And those who could not fill up the feedback link, you don't need to worry. We will share the link to the participant later. And on behalf of NIDM and NRSC, we wish all the participants a healthy and safe life. As दो गज की दूरी बहुत है जरूरी to reduce the COVID-19 spread. Let us all do our part at individual level fight this global pandemic. Stay healthy, stay safe. Thank you. Now I request host to end the meeting.
Okay, Dr. Hatchko. So I will just keep it open for 2 minutes so that if some participant they haven't fill up the feedback form, let them fill up the form. I will within 2 minutes, ma'am. I will close it. Thank you.
Okay, thank you, Raju.